Hello, welcome back. The title of this lesson is actually called Using Measures of Variability in Data. A better title might be Understanding the Spread of Data Using Different Calculations. And really, the super long-winded title would be Comparing the Range of Data to the Interquartile Range of Data, and also comparing it to the mean absolute deviation. You can see why I didn't title it like that, because it's just too long. But basically, we have learned now to calculate how spread apart our data is by three different ways. We have learned to find the range of the data, the two endpoints, subtract them. We've calculated the interquartile range, so we had to find the quartiles and subtract that to get a spread of the data. And then we just now learned how to find the mean absolute deviation, which is on average how spread the data is about the mean. So here in this lesson, we're going to present data, and we're actually going to calculate all three of those and put them all three on the same graph. We've done everything in this lesson already in previous lessons. There are no surprises. It's literally a summary lesson because I really want you to be able to see what they all look like, right? So this is one of those rare opportunities where I'm going to show you the answer before we do the actual work, because I want you to see up front what the answer looks like. So here we have our typical line plot. I'm going to give you the data in just a second, but you can see the black dots are the data points. And we have lots and lots of data here. This is why it's kind of overwhelming, but basically we have the mean that we're going to calculate, right? And then we have the range of the data, which is the range, which is the big value minus the small value. And then on here, we have also the interquartile range shown on here. And then we also have the mean absolute deviation. In this case, it's plus or minus 2 about the mean. Now, all three of these methods, the range, the interquartile range, and the mean absolute deviation, they're just three different ways of expressing how spread your data is. For all three of them, the larger the number, the more spread out the data is, right? They're literally just like variety is the spice of life. We don't all eat vanilla ice cream. Some people like chocolate, some people like strawberry. Later on, when you're doing real work with real data, sometimes you'll need to calculate the range, and sometimes you'll use the interquartile range, and sometimes you'll use the mean absolute deviation. One thing I did not put on here is we did also talk about the standard deviation, which is very closely related to the mean absolute deviation, and we sometimes use that also. I just wanted you to look at this to see how they all compare, and just notice that they're all similar calculations. 4.5, the MAD here was 2, which is when you look at plus 2 to minus 2 is 4, and then the range is 6. They're all similar numbers. Now let's take a look at our actual data for problem number 1. Now, let's say this is the age a child learns how to ride a bike, right? 17, 12, 11, 11, and 14, right? So some people learn older and some people learn younger. So the first thing we generally want to do is we want to write our data from least to greatest. We've been doing that every single time. So let's do that, right? The smallest number that we have here is 11. So I'll put 11 here, and then another 11. And then we have a 12, and then we have a 14, and then we have a 17. So 11, 11, 12, 14, 17. First step, 11, 11, 12, 14, 17, is just plot the data. 11, 11, 12, 14, 17. So the black dots just are showing where the data lies on the chart so you can visually see how spread the data is. Now let's calculate the first method of measuring the spread of this data, which we call the range of the data. Right? The range of the data is the largest number minus the smallest number. So 17 minus 11 is 6, and so the range of this guy is equal to 6. So on our chart, we can just draw a curly brace that extends from the largest number all the way to the smallest number, and then we can see that the range is equal to 6. It is literally telling us how broad the data is because it is showing us the envelope in which all of our data lies. All right, now that we know the range, let's move on to the interquartile range. Remember, the range of the data, it does tell us how broad the data is. However, if we have outliers, like take a look at this number 17-year-old, the 17-year-old who learned how to ride his bike. The range is all the way from the biggest to the smallest. So if you have an outlier, then it can drive, you might think that your range is bigger than it really is because that one point is driving the calculation. So what we want to do is find the interquartile range. Right? We're going to do that here. First, let's again list the data from least to greatest. So we'll have 11, and then we'll have 11, then we'll have 12, then we'll have 14, then we'll have 17. Okay. Now the first step in finding the interquartile range is to find the median of the whole data set. So we look in the center and we see a number 12 here because we have data on the lower end and data on the upper end. If we pull it apart, we see that we have a 12 right here. And we call the median here for this calculation, we call it Q2. So the median is the center value of the data. We rename it Q2 when we're talking about quartiles, right? By the way, I'll just stop here and say, if you're looking at any of this and it seems like, oh, how did he do that? It's just because I've already covered everything in this lesson in previous lessons. So I'm going a little faster. I'm not doing quite as much explaining because we've already covered it. So if you're looking and you're like, how do you do that? Please go back and watch the dedicated lessons. We have separate lessons for each of these. So here is quartile number 2. Now, how do we find quartile, the first quartile and the third quartile? Well, we look among this data here, we try to find the number in the middle, but both of them are the same. So in order to find the middle value, you average these two numbers, but when you average 11 and 11, you just get 11. You add them up, divide by 2, 22 divided by 2 is 11. So the answer here, Q1, is equal to 11. You add up, divide by 2. And then over here, same sort of thing. If you add these and divide by 2, you're going to find that Q3 is equal to 15.5. Just add both of these numbers up, you're going to get 31. And 31 divided by 2, you'll get this. Another way of looking at it is, what comes between 14 and 17? So you have 15, and then 16, and then 17. So right in the middle is 15 and a half. So that's Q3. And then, if you want to figure out the interquartile range, all you do is you take the Q3, which is 15.5, and you subtract away the Q1, which is 11. So 15.5 minus 11, interquartile range is equal to 4.5. 4.5. And when you look over here, Q1 is 11, Q3 is 15.5, Q1 is 11, Q3 we put here on the chart at 15.5, and the difference between them is what we call the interquartile range at 4.5. Notice that the interquartile range is pretty close to the regular range, but notice that it's smaller because the regular range is looking at the most extreme data points, where the interquartile range is subtracting the quartiles, and you're kind of throwing out any outliers. This 17 is almost like an outlier. So the interquartile range is used when we really don't want to emphasize any outliers when we're trying to figure out the spread of the data. All right, now what we want to do is figure out the mean and the mean absolute deviation of this guy. So the mean of this data, the mean of this data. The way that you calculate the mean of this data is you have 2 points at 11, 1 at 12, 1 at 14, 1 at 17. So you add 11 plus 12 plus 14 plus 17. You add all those numbers up, and what you're going to get is 65. And you divide by 5 because you have 5 data points. So you add up all the data points, divide by 5, and you're going to get 13. And so on this chart, we mark the mean exactly at 13 because that is where we calculated the mean to be. Next, we have to calculate the deviations of each point subtracted from the mean, subtracted from the mean, subtract from the mean. And we take the absolute value because the numbers that are below, they're really negative deviations because they're below the mean, but we strip away the signs by looking at the absolute value. So for those deviations, right, the way we do it is we say, for instance, 17 minus the mean, 17 minus 13, right? And that's going to be 4, and the absolute value of 4 is 4. And then for the next point, we have 14 minus 13, right? 14 minus 13. And that's going to give you 1, and the absolute value of that is 1. And then we have 12 minus 13, right? So I'll go over here. I'll say 12 minus 13. Now, this is going to actually give us negative 1 because it's smaller, but when we take the absolute value, we get a positive 1. And then finally, we have 11 minus 13. That's 2 units down. So 11 minus 13 is going to give you negative 2, which when we take the absolute value is 2. You can subtract them in your mind. 13 minus 11, you get 2. Put a negative sign on it because it's backwards, and then you take the absolute value. And then we have one more, 11 minus 13, and we also get a 2 from that because we had 2 points there. Now that we have all of these deviations, the mean absolute deviation is just averaging these up. So really all we do is we take the 2 plus the 2 here, and then the 1 from here, and then 1 from there, and 4 from there. We add these numbers up, and we divide by 5. And this is 4, 5, 6, and then 10, divide by 5, and then we get 2. So the mean absolute deviation is 2. So if the mean was here, mean absolute deviation of 2 means that 2 points above the mean is 15 and 2 points below the mean is 11. That means that most of our data points will be between the range of 11 and 15, plus or minus 2 from the mean, right? And the mean is at 13. So we're going to do more problems, but I really want you to look at this one carefully and soak it up, because you know, it's very easy to get confused. We calculate the range, and we calculate the mean absolute deviation, and we calculate the interquartile range. Later on in math, we do more with the standard deviation, and there's even something called variance we look at later on. And they're all just different ways, different flavors of expressing the width of the data set, and they all have their own calculation. So don't try to pick one and say which one's right. It's not that which one's right, it's just that they're all different ways of doing the same thing. The range really does express how wide the data set is, but if you have an outlier like this one, then it kind of, it doesn't make as much sense to include it, because the range of the data, while it is true, you're letting one data point drive the range. The interquartile range throws away the upper and the lower quartiles, as we said before, so you get a smaller number and it might be more representative of your data. But then we can say the mean absolute deviation is on average plus or minus how many units around the mean does most of our data lie. So let me take this one down. We'll do another one and get a little more practice with comparing these measures of variability. All right, let's take a look at our next set of data. We have the numbers 25 and 22. Another 25, 25, 24, and 23. These are the survey results among pilots at the age they first learned to fly an airplane. Okay, so let's first work on calculating the range of this data. We're going to arrange it from least to greatest. So the smallest number on this list is 22. And going up from there, we have a 23-year-old, right? And then we have a 24-year-old right here. And then we have 25, 25, 25. So at the end, we have 25, 25, and 25. So 22 to 25. Now, before we do anything else, let's plot this data. We have 22, 23, 24, 25, 5, 5. 22, 23, 24, 25, 5, 5. Now, I know this chart looks busy. I want you to ignore most of it, but I want you first just to focus on the fact that these are the data points that have been represented there. Now, to find the range of this data, which is one way to measure the spread of the data, we take 25, the largest number, and we subtract 22. And so the range of the data is 3. So on this graph, this is how we express it. We have a curly brace from the extreme of the largest data point to the smallest data point, and the range really does express the true and total width of all of our data points, okay? Again, the problem with the range is, what if you have some incredibly young person at 13 years old that learns to fly? It's an outlier, and then the range of your data would be much bigger. It is true that that is your data, but if you have really rare data points or maybe errors in your data, then the range will reflect that, because it's driving the range. The extreme points are driving the range. So this is one way of measuring it, but we don't always like to do that. So let's go and calculate the interquartile range, which you can already see we're going to get a smaller number. It's going to be 2. So let's calculate the interquartile range. All right, first thing we need to do to calculate the interquartile range is we rewrite the data from least to greatest. So we have 22 followed by 23, if I can write 2 correctly. Okay. Then we have 24, then we have 25, 25, and then finally 25. So we have 22, 23, 24, 25, 5, 5. All right, first thing we do is we always try to find the median or the center value of the data set. So we have 6 data values here. So if we group these together and we group these together, so we have 3 and 3, there is no central point in the data set. There is no central number. But what we do to find the median then is we just take the 2 middle numbers and we average them. Now you could take 24 and add it to 25 and divide by 2. You'll get 49 and you'll divide by 2. And the answer you're going to get for Q2 is going to be 24.5. But you don't have to always do that work, because the average of these numbers is what is in the middle. 24 and 25 in the middle is 24.5. So that has to be Q2. All right, now we go over and take a look at the lower part of the data and find the median of this, which we see we have a middle value of 23. So we say Q1 is 23. And over here we have a middle value of this data, which is Q3, is 25. So here we have this. So now we know that Q1 is 23 and Q3 is 25. Those are the upper and the lower quartiles. And then the interquartile range is just the subtraction of 25 minus 23, the upper quartile and the lower quartile, which is just 2. So the interquartile range goes from 23 to 25, from 23, Q1, to 25, Q3, and we subtract them and we get an interquartile range of 2. So notice what you're doing is you're taking the quartiles and you're ignoring anything beyond it, any extreme outliers, and you're only subtracting those guys. And so that's why the interquartile range is a little bit smaller than the range of the data, because essentially you've ignored this outlier down here. And so it's a more accurate representation of the bulk core of your data that's kind of clumped together. So the interquartile range being 2 here. All right, now let's go and calculate the mean and then the mean absolute deviation. So for the mean of this data, we've done it so many times, I'm not going to do it over and over again. But in order to do it, you just add your data points and divide. 22 plus 23 plus 24 plus 25 plus 25 plus 25. When you add all that stuff up, you're going to get 144. And there's 6 data points, so you'll divide by 6. And you're going to get an answer of 24 for that. So the mean of this guy is 24, and that's why I have an X here at 24. This is the mean. The mean is 24. Now we have to find these deviations, these absolute deviations, right? So what we want to do is take a look at 25 minus 24, but we have 3 of them. So what we're going to do is 25 minus 24 is 1, and the absolute value is 1. We're going to have 25 minus 24, and the absolute value of that is 1. 25 minus 24, and the absolute value of that is 1. So we get all 1s. Now we have this data point minus the mean, so we're going to have 25 minus 24. The data point's at 24 minus the average, which is also 24, and you get a 0. Absolute value is 0. So this data point doesn't have any deviation from the mean. Now you have a point lower, 23 minus 24. 23 minus 24. And this is going to be negative 1, the absolute value of which is 1. Because in your mind, you can flip it around, say 24 minus this is 1, but you have to put the negative on it because it's backwards, and then you take the absolute value, you get negative 1. This just means it's 1 distance unit away from the mean. 22 minus 24. 22 minus 24. Same thing in your mind. Subtract it the correct way, you get a 2, but because it's backwards, you put negative 2, and then the absolute value of that is 2. So here's all these deviations, and now the mean absolute deviation, we add them all up. 2 plus 1 plus 0 plus 1 plus 1 plus 1, all of these, and we divide by 1, 2, 3, 4, 5, 6. And what do we get when we add all of this stuff up? We have 2, 3, 4, 5, 6. Divided by 6, and so the mean absolute deviation is 1. So the mean absolute deviation is 1, and that means that 1 unit above the mean and 1 unit below the mean, this is what the plus or minus 1 is where most of our data will lie. So between 23 and 25, the majority of our data will lie. So in this case, the interquartile range of 2 lines up with the range that we get from plus or minus the mean absolute deviation. And the range of 3 is also not that different. And the reason all 3 of these numbers for the measurement of the variation of the data isn't that different is because we don't have any outliers. If we had extreme outliers, then these numbers would be, or if we had clumped data in different areas of clumping, then we could see significant differences between them. But they're just basically 3 different flavors of calculating the spread of this data. So I'd like to take this down and do one more and call this lesson a day. All right, let's take a look at our last bit of data in this lesson. This is the number of lemons on various lemon trees. So one tree had 17 lemons, another tree had 13 lemons, and then 9 lemons on another, 12, 14, 12 lemons, 17, and then 18 lemons. 1, 2, 3, 4, 5, 6, 7, 8. And we have 8 lemons in our data set. So let's arrange it from least to greatest. The smallest number is 9. And then after that, we had 12 and then another 12, right? And then 13 and 14. And then 17 and 17. And then 18. All right? So we had 9, 12, 12, 13, 14, 17, 17, 18. So let's plot this data. So we might want to write them down as we scoot over and take a look at it. 9, 12, 12, 13, 14. 9, 12, 12, 13, 14. And then after 14, 17, 17, 18. 17, 17, 18. So this is the data there. And now we want to calculate the range. We want to take the largest value and subtract away the smallest value. So the range of this data is just equal to the biggest value minus the smallest value, which is 9. So the range is 9. And you can see that that's what we have here with the green curly brace. The range is 9, meaning the largest value minus the smallest value gives us a range, which is exactly what it says, of 9 units from the smallest to the largest value. Now again, if you had an outlier with a lemon tree with 100 lemons on it, that would be an outlier way to the right, and our range would be really, really big. Even though it was only one tree, it's important, but it's also just one tree, so we may not want to count it so heavily. So let's go calculate the interquartile range. Let's write down the data again, least to greatest. We had 9, and then 12, and then 12, 13, and then 14, and then 17, and then 17, and then 18. All right. Now we need to find the median, which is the center of the data. 1, 2, 3, 4, 5, 6, 7, 8 means we have 4 lower numbers and 4 upper numbers. So we really don't have a good center value right in the center. So what we have to do instead is then average 13 and 14, and the median Q2 is going to work out to be 13.5. You don't even have to calculate to really do it, because all you have to do is say what's between 13 and 14, 13.5. If you want, you can add them. 13 plus 14, you'll get 27. Divide by 2, you'll get 13.5. Now we go and take a look at the lower half of the data and figure out, okay, what's the median of this? Well, again, there's no center value because you have 2 points here and here. So instead what we need to do is we need to average the 12 and 12. But again, when you average the inner two numbers, but when you average them, you just get the same number, which is Q1, which is 12. If you add 12 and 12, you get 24, and then divide by 2, you get 12. Same thing here. These inner two numbers, we don't have a single center, so we add them up, divide by 2, and you're just going to get Q3 is equal to 17. Same sort of thing. You'll get 34, and you'll divide by 2, and you'll get 17. So now that we know this, the interquartile range is just equal to Q3, 17, minus Q1, which is 12. And you'll get an answer of 5. So this interquartile range is 5, and it goes from Q1 of 12 to Q3 of 17. Q1 of 12 to Q3 of 17, when you subtract them, the interquartile range is just 5. So it's just another way of expressing the spread of the data when we kind of discard the outliers. In this case, this is kind of an outlier. Most of our data is over here, so we don't really consider that with the interquartile range. And so the ICQ is 5, which is quite different than 9, because this one tree that didn't bear much fruit, it shouldn't drive the calculation for the breadth of our data when it's really only one tree that does it, right? So we don't emphasize it as much with the interquartile range. Finally, let's go figure out the mean and the mean absolute deviation. For the mean, all we have to do is we add all these together. 9 plus 12 plus 12 plus 13 plus 14 plus 17 plus 17 plus 18. We add them all up, and when we add them all up, we get 112, and then we have to divide by 8 data points, and so the mean actually works out to be 14. So 112, when you add them up, divide by 8, you get 14. And so the mean, we can put a little x here, the mean is lying right here at 14. You can see the mean is equal to 14. All right, next, let's find the deviations of all of our data points. All right, so we have 18 minus the mean of 14. 18 minus 14. That's a difference of 4, so the absolute value is, again, 4. 17 minus 14. This is 3. Take the absolute value, you get 3. But we had 2 of those points at 17, so we have to have both of them here, and we just get 3. Next, we have a point at 14, but that's just the same number as the mean. So 14 minus 14, you get 0, which means your mean absolute deviation is 0. 13 minus 14. 13 minus 14 just means it's 1 below the mean. So really, you get -1 when you subtract, which means the absolute deviation is just 1. It just means it's 1 unit either way, plus or minus the mean, which is, in this case, it's minus. So you could say 14 minus 13, you get 1. You got to put a negative sign on it because it's backwards, and then the absolute value is 1. 12 minus 14, we have 2 of those. 12 minus 14, you're going to get negative 2 when you do the same thing, which gives you a positive 2 deviation. You have another point, 14, and then you're going to get negative 2, which means you have 2. So again, you're 2 units down below 14, so you get a difference of negative 2, and then the absolute value is positive 2. And then finally, you have 9 minus 14. 9 minus 14. Right? And you get negative 5 here, because it's 5 units down below. And when you take the absolute value, it's 5. So these are all the deviations. And so for the mean absolute deviation, we just add them all up. We say 5 plus 2 plus 2 plus 1, and then 0, 3, 3, 4. 0, 3, 3, 4. Add them all up, and we have how many of these? 8. So we have to divide by 8. And so the mean absolute deviation, when you add them all up, you get 20. And you divide by 8, and you convert to a decimal, you're going to get exactly 2.5. 2.5. So what it means is the mean absolute deviation is plus 2.5 and minus 2.5 about the mean. So the mean absolute deviation is 2.5. 2.5 units above the mean is 15, 16 and a half. And down below to between 11 and 12 is 11 and a half. So between 11 and a half and up to 16 and a half was plus or minus whatever our MAD was. That's where most of our data lies, and that's what we see here. Now we do have a couple of data points a little bit outside, but that's how the calculation is. In some data sets, one of these measures is going to make a little more sense to use than others. Now, we're not getting into all that now. It really depends on what your data looks like, how many data points you have, the quality of the data, do you have any outliers? All of those questions as far as like what do you use in real life, it really just depends on the problem. Here, we're just trying to show the difference between them and to show them on one chart, to show that the range is so big because it goes all the way across the data. The interquartile range is smaller because it throws out that data. And then the mean absolute deviation, which is just showing where most of our data lies, is among basically the same, because plus or minus 2.5 is 5 units. So it's still 5 units, same as the IQR. So sometimes we will use one, sometimes we will use another. I would like you to go back and calculate all of these yourself. We have one more lesson on this, and I promise we'll be done with it. So calculate these, follow me on to part 2. We'll wrap up the concept of comparing and using the measures of variability.